In the continuing theme of writing stoichiometry problems until there's no more stoichiometry problems in the world to do, I came up with these which give a little bit of variety, like this one says, you're given an excess amount of barium hydroxide and a specific amount of excess, and then you have to come up with that. And in this one, it's you're given an actual yield, assuming 100%, and then you got to come back with everything. And actually, like, both of these are much faster than they look. This one, faster than either of them. So we're going to follow our basic steps like before. In this particular case, we've got a mass collected in lab, which would be an actual yield. But if we got 100% yield, that's also our theoretical yield, which we can then use to get everything else. So we'll start with this problem because I'm most awake on that one. We've got 712 grams, and we're going to be dividing by our molar mass, which is 325.33. All right, that's the AlClO43 aluminum perchlorate. And again, 325.33. This is going to give us the amount that we have, and I'm going to carry that down and stop crunching things all into one place on the page. That's 2.19 moles of the aluminum perchlorate, 2.19 moles, AlClO4, 3. Okay, that is what we have. And we're going to kind of brute force this into what we need or what we used, but I'm going to do it all in one box, right? Like, if you know any one of these amounts, you know all of these amounts, and we know one, so we can get all the other ones. The only annoying part is we're going to have to turn those into masses, right? Have to turn it into masses. But we need a mass of the other products, right, which are the CO2 and the H2O, and we need a mass of each reactant, which are this and this, and we know that right there. So let's make it happen as quickly and painlessly as possible. This is a yield. I should have done it in blue or purple there, so let's start with that, and we'll work our way backwards. We've got 2.19 moles of aluminum perchlorate. And now the stoichiometry begins, in fact. Hopefully I've left myself adequate room to use a decent font. We want to find out about 1, 2, 3, 4 things, so I'm just going to list those 4 right there. I'll pick some hopefully visually distinguishable colors, and we'll see how this goes. So the first thing I want to know about are the other products, and there's CO2 and H2O. So 2 moles of that, we've got 3 moles of CO2. All right, I should have put that 2 right there. 2 moles of aluminum perchlorate. And that's from the balanced chemical equation. In fact, everything after the line, right, after the first box, comes from the balanced chemical equation. This will be, with our 3 moles CO2 times the 2.19 divided by 2, we end up with 6.57 moles of CO2. 6.57 moles of our CO2, all right? And then we can turn that into a mass by multiplying by molar mass. In fact, let me just do that right now. Times our 44.01 grams per mole. And we should end up with, in this case, 289 grams of CO2. 289 grams of CO2. So that's the mass of one of the products. And now we need the mass of the other product. And that is H2O. There's 3 moles of H2O. It's convenient that this is the same number then, 6.57 moles of water. But instead of multiplying by 44, we're going to multiply by the molar mass of water, which is 18.02 grams per mole. And so we end up with 118.3, I'll just say 118 grams of H2O. All right. In terms of like maybe keeping track of this, that is the mass of the other products formed. And that's our answer to part A. For part B, we want to find out about the starting mass of each reactant. This is how much we made. It's a theoretical yield. We just work our way backwards. Again, we now know this, so we can use a ratio to get back to there. And in this particular case, we can sneak in right there some other colors, like this beautiful lavender. We want to know about the aluminum carbonate, so we've got 1 mole Al2CO3, and that'll give us 2.19 moles of aluminum carbonate. We'll multiply by its molar mass, which was 234 approximately grams per mole, and we should end up with 512 grams. 234 grams. We end up with 512 grams. All right, last one here. We've got 6 moles of perchloric acid. So that's going to give us 13.1 moles HClO4. We want to get a mass of that. We'll multiply by our molar mass, which is 100.46. And that gives us 1320 approximately grams of perchloric acid. And again, that number is pretty high compared to the other ones because it's got a pretty high molar mass compared to the water or the CO2 at least. And we got 6 times as many moles as the aluminum carbonate. So it does seem reasonable. All right, we've got, there's my evil blue highlighter when I need it. Here's pink. This goes with these two, and we're done with that example right there. We could have written a lot more, but we didn't have to. In fact, I snuck in both reactants and products right in there into one grid. Let's take a look at this other one as my brain is slowing down more and more and more. It's been a long day. In this one, the only thing that's really different is we're given a starting mass of the barium hydroxide that is 54 grams excess of what we need. All right, so that's kind of weird. It's just a variation on these stoichiometry problems. Let's make this happen quickly and painlessly. 127 grams of this, 54 grams over the amount we need. So I'm just going to start with that 127 grams of acetic acid. We'll divide by its molar mass, 60.06. That is also known as like a dilute solution of acetic acid, around 3% solution, is vinegar. So if you're ever wondering why that compound keeps coming up, that's why. All right, 127 over 60, we get, in this particular case, 2.11 moles of acetic acid. And this is what we have. Similar to this problem, I want some more space so we don't have to smush our font. This is a reactant, so I'm going to stick with the red color as we do this. And I'll write it over here. We don't need a ton of space, but I do want to set things up in a certain way. 2.11 moles CH3COOH. It is the night for markers falling apart. Okay, we know that for every 2 moles of acetic acid, what do we want to know about? Well, we want to know about the barium hydroxide, and we know it's 54 grams over what we need, and we want to know about the water, and we have a percent to go along with that. So we only need to do 2 comparisons here. We only need to know about the barium hydroxide and the water, and so we don't have to worry about the barium acetate. Let's get some colors moving here. We know that for the barium hydroxide, we've got one of those, so 1 mole barium hydroxide, and that'll give us 1.06 moles of barium hydroxide, which we then multiply by its molar mass, and for barium hydroxide that's 171.35, and that gives us 181.2 grams, and this is rather important. So we have 181.2 grams of barium hydroxide. And that's what we need. And we have it. In fact, we have 54 grams above that. So to get the answer that we need here, I'm just going to do what it says, which is that's what we need plus 54, and that's going to give us our 235.2 grams. And that is one of our answers. It isn't super pretty in that color, but we've got it. All right, one down. That's 235.2. Now that I wrote directly over that and it's not visible, let's take care of the H2O. As we look at our H2O, we can get a theoretical yield, and that theoretical yield is going to be based on the 2 moles of H2O. So we end up with 2.11 moles of H2O. This times 2 divided by 2. We're going to multiply by the molar mass, which will give us, in this particular case, 38.11 grams of water. Now this isn't the answer to anything, but that's a theoretical yield. And we can turn that theoretical yield into an actual yield using the percent yield equation. And our color scheme has gone straight out the window, but I'll see what I can do. We know percent yield is supposed to be the actual, right, over the theoretical times 100. In this case, we're going to use that as a checklist. I know the percent yield. It is 89.0%. I know the theoretical yield, and I want to find the actual yield. So the actual yield is going to be the percent over 100 times our theoretical yield. We have 89.0%, so we'll take 0.890 times our theoretical yield, which was 38.11 grams of H2O, and we end up with 33.92 grams of H2O as our actual yield. And pink highlighter on that, a little box around it or wherever. And that is that example. We're in the home stretch for stoichiometry examples. I want to do a couple 3 reactant problems and then we'll be done.